Okay, so the next topic is, or the next part of the discussion is large scale relative to the flame thickness, or what I would be referring to as the hydrodynamic theory. The idea is the following. You see, we have seen that that's basically the structure of a premix flame, where the temperature rises from the unburned to the adiabatic temperature. The reactant is being consumed, and the reaction occurs in part of that scale, which is the flame thickness LF. By the way, I forgot to mention something which is rather important. So let me say it now. We have seen that the asymptotic theory of the premix flame gave us a temperature profile which is of this form. Well, it depends on what unit, but well, let me put it scaled. So it's 1 plus Ta minus 1 e to the x, right? This was the preheat temperature, the temperature in the preheat zone that rises from 1 to Ta, right, the adiabatic temperature. And remember, we scaled everything in terms of LF, which is the thermal diffusivity divided by the laminar flame speed, which is a diffusion length. And the comment I want to make is about the actual thickness of the flame. So, well, what you see from the exponential is that the distance from the flame temperature, Ta, up to where, well, of course, in my one-dimensional model, it's all the way to negative infinity, but it takes approximately 5 to 6 units of length for the exponential to be practically 1% from the cold temperature, from 1. So you would argue then that the true thickness of the flame is about 5 to 6 LF, okay? Now, people sometimes criticize saying, oh, but your flame thickness is LF. No, that's a representative parameter that I use for non-dimensionalization. My flame thickness is 5 LF or 6 LF. Numerically, people don't, what people do typically is, since you have a curve that has an inflection point, people take the inflection point and take the slopes where it cuts the two ends and define that as to be the thickness, right? And so neither one is exact, but they are representative of the flame thickness. I just wanted to bring that to the attention because we are talking about flame thicknesses. So anyway, the thickness of a real flame is rather small, and it's about a fraction of a millimeter to a millimeter at the most. And so this is the gray region here, and that's where most of the combustion occur. So this now, let's suppose that we look at this on a much larger scale. Then this gray region will be seen to be a very narrow region, or a boundary layer, where the temperature essentially jumps from the cold to the hot value. The mass fraction is getting totally consumed, and clearly the density will go from the unburned to the burned value. Well, it's going to be higher here and lower here. So on the larger scale, on a large hydrodynamic scale of a few centimeters and so on, the flame can be seen as a hydrodynamic discontinuity, or a density discontinuity. And this is really what I want to exploit in this lecture. It's this view of the flame in a hydrodynamic field, which is of a much larger scale. So here is the idea again. Delta will be the parameter which represent the relative ratio between the flame thickness and the hydrodynamic length. Typically, it's a small number, as I said. So here is my flame, and everything that is occurring here is that structure that we have discussed before, right? And that's about LF. The unburned gas has a density rho u, and the burned gas has density rho b. So the entire flame, which is both the preheat and the reaction zone, in this context is seen as a thin region, which in some limit it's going to be a surface or a sheet or a flame front. Before I define that, it's important to define what we call flame speed, okay? This is the standard convention definition, but not everywhere, as usual. There's always places where define things differently. So, so the flame speed is defined as the propagation speed relative to the fresh gas, relative to the incoming gas. So in my notation, and I will be consistent with that notation all this week, the normal is pointing toward the burn gas, the unit normal. Note that the flame is not necessarily flat. In a three-dimensional flow, it will be whatever it is. And the propagation speed is Vf. In other words, propagation speed is the speed that the interface that you see here, let's say the reaction sheet, propagate relative to a fixed coordinate system. And the gas is coming at a velocity along the normal. The component is Vn. So the flame speed is the relative velocity, minus Vf plus Vn. Minus because my normal is in the burn gas. So in other words, if the gas is at rest, the flame speed is Vf, clearly, right? Okay. I said that not everywhere they define it this way. Some paper in the former Soviet Union that define flame speed relative to the burn gas. Okay? Of course, there is a relation between one and another, and sometimes we will see that that comes out, but one have to be careful of the definition. Now, as I wrote here, this is a very nice definition, but it's ambiguous. Because unlike you tell me what is the surface that you are focusing on, it's meaningless. To say the velocity of the flame, okay? The flame has a thickness in reality, and the velocity changes across from one location to another, and so this definition is ambiguous unless you define very precisely the surface. In the asymptotic sense, when the entire flame shrinks to a surface, there is a precise meaning to flame speed. And I'm going to show you later, not today, but tomorrow, what kind of ambiguity you get by identifying the flame surface as, for example, an isotherm of temperature T.3 or T.7, okay? There's a difference. And in fact, some of them will give you the wrong answer. So one have to be careful about this. Okay, so since at the moment we are in the asymptotic limit, that delta goes to 0, there is a clear choice where, or there is a clear choice what that surface is, and that unique choice gives us a unique value for the normal and a unique value for the propagation speed Vf. This is nothing more than a geometric factor. It just tells you that those points propagate in the normal direction at that speed to retain or to remain on that surface. Okay, and the flame speed, therefore, is uniquely determined as I did here, and I will always use it relative to the unburned gas. Okay, what is now? Okay, another comment to make before moving on is that the expression here, by the way, I said that that's a definition of flame speed, but I didn't say what the flame speed is equal to, right? But once this is known, then this statement here is equivalent to an evolution equation that tells you how the flame move, or what is the shape of the flame at different time. So an expression for the flame speed or the evolution for how the flame evolved is equivalent statements, okay? This is an evolution question, tells you that F changes in timeline. Note that it depends on the flow, which in reality, due to combustion, is changing, right? Combustion affects the flow. So this is not a simple equation to solve. It's coupled, highly coupled to the entire flow field and the combustion field. And this SF, at the moment, we didn't say what it is, okay? And by the way, this comes from simply substituting for VF this minus dF dt gradient F, the norm, and for the N, right, this quantity. So it's just a simple substitution. Okay. By the way, this equation is often known in the literature as G equation. I'm not particularly fond, G equation. I'm not particularly fond of that term, but this equation, despite the fact that people call it G equation and refer to particular papers here and there, was written much longer by Markstein in 1950, and he used F. So I follow Markstein. Okay, I don't want to call it the F equation either. So how does the propagation speed SF depend on the local flow and on the mixture condition, right? That's the question. The answer to this is that we don't know. Okay, we don't know how it depends in general. What we do know certain things. So in the early studies, perhaps the earliest studies that try to incorporate fluid mechanics to the flame, I mean, flame propagation were studied by Matalon and Le Chatelier since the 1800 or 1850, and by various people since. But the incorporation of hydrodynamic effect perhaps started with Darieux in France. It was a French engineer and the famous Landau, the theoretical physicist, in the 1940s, in two separate papers that were published almost simultaneously. Darieux's paper was never published because of the turn of the war, but it was presented at a conference just in 1938, and many people in the community have copies of it, including the letter that he submitted the paper to publication, which is actually interesting to read. Landau's paper is not only published in a journal, but also appear as an exercise in his famous book, Hydrodynamic. I think it's called just Hydrodynamic or Fluid Mechanics, something like that. So many of Landau's exercise in the book are in fact papers somewhere. But anyway, the idea of Landau and Darieux, they say, well, the curved flame propagate locally, right? The local flame speed is the laminar flame speed. They did that because they were interested in studying the stability of planar flame, something that we will discuss probably on Thursday. Tomorrow? Okay, maybe. And that was the assumption there. But as you will see in the discussion then, there were difficulties, and therefore Markstein tried to argue that, well, the speed can also depend locally on the local curvature. And so he introduced this phenomenological expression and a coefficient here, which today we call Markstein length. But at the time, it was introduced just as a coefficient, phenomenological coefficient, with a dependence on curvature, kappa, curvature of the flame. Well, more recently, and that's the subject of tomorrow, we know that, or we can derive a more systematically an expression for the flame speed which is of the form laminar flame speed and a correction due to what we call flame stretch. And I will talk tomorrow about what flame stretch is and what's the meaning of that is. But one of the advantages of deriving such an expression is that the coefficient L is no longer a coefficient phenomenologically obtained, but has been derived and has shown to depend specifically on quantities like diffusivity, thermal expansion, etc., etc. Okay, so this is a theory which is built on, it's an asymptotic theory which is built on the idea that the stretch rate is, or the flame is thin, or the stretch rate is weak. So for weak stretch rate, for weakly stretched flame, we know that the dependence of speed on the local flow and mixture condition is of that form. But if the flame is not weakly stretched, we don't know in general. Of course, there are particular cases that are addressed numerically, but there is no general theory or general understanding of that dependence. Okay, so this is the first question. So this is what I say is not generally known. Most of today, what I want to focus on today will be just on using the Darry-Landau assumption in understanding the effect. In other words, we are only going to use the order 1 effect of the flame. So here is a little comment about the ambiguity that you will find if you try to define it numerically. So numerically, the ambiguity that you face when you want to define flame speed numerically. So what you would do numerically, you say, okay, I'm going to choose a certain isotherm to be representing of the flame surface. So then your normal and the propagation speed is of that isotherm, okay? And then what I have called flame speed, usually called in the literature displacement speed, which is the same thing. It's the speed of that isotherm. And then you compute, you can compute this in multiple ways. You can compute it either from the kinematic relation, right, that the displacement speed is the velocity of that interface relative to the gas, or if you use the one of the energy equations, since this term is usually, or dt by dt without that gradient, appear on the left-hand side of the equation, then you you have anyway computed this in your code, so you use all the right-hand side to compute SD. So those are different ways of computing it, but usually it's make reference to a particular isotherm. Of course, it doesn't have to be isotherm. It could be also the location of a certain radical, or the contour of a species at a, but it's the same idea. It's the same ambiguity that you will find. So I have only posed here the question, which is the correct location? We will talk about that tomorrow. Okay, so now consider the first order approximation due to Darry and Landau. The idea is that you would have the flame is thin, so all viscous effects, you see, viscosity, diffusion effect, reaction, they are all small of the order of the flame thickness and therefore negligible to leading order. And so if they are negligible, what you are left is with Euler equation. If you include gravity, then you also have gravity. I think the G here is missing. Okay, it should have been rho G, not rho EG, or rho G EG, whatever. I think it's clear, you can fix that up. And then for the species and the temperature, you just have that the material derivative is 0. Material derivative is 0 means that the fluid retained their temperature. Okay, so if you assume that the mixture is homogeneous, it has a given amount of reactant in the fresh mixture, all the fluid particles retain that value up to the flame. Okay, same thing, they retain the temperature up to the flame. So the temperature remain constant and the mass fraction remain constant, YU and TU. What happened behind the flame? Well, the mass is all consumed, so y is 0. So again, it retained the y equal to 0 everywhere. It cannot be created again. What about the temperature? Well, the assumption is, remember, it's an assumption that the temperature at the moment, it's an assumption the temperature remained the adiabatic temperature everywhere, and therefore, if it's a constant along the flame surface, every fluid particle retained that temperature behind, and so temperature behind is the adiabatic temperature. And so based on this simple idea or theory, the density, temperature, well, density is the reciprocal of temperature, so it goes hand by hand. So the temperature, density, and mass fraction are piecewise constant function, unburned, burn, and the remaining is to solve the Euler equation on either side with some jump relation across. Here is the sigma that I did not define before. Now it's very important. Sigma is rho u over rho b, Tb over Tu. It's a thermal expansion parameter. Some people like to call rho b over rho u the thermal expansion, which is of course going to be a number less than 1. And some people like to call 1 minus that the thermal expansion. So it doesn't matter, but be careful of the definition. Okay. Tb is, as I said, assume the adiabatic temperature. So mathematically, we are faced with Euler equation. Now, this is not an incompressible flow. This is also not a compressible flow, because compressibility is long gone by assuming zero Mach number approximation. This is what we call a variable density flow. And a lot of people call this compressible, but it's really sending the wrong message because there's no compressibility here. Okay, so this is the equation. What are the jump conditions across the interface? We have gone through that earlier. It's the Rankine-Hugoniot relation, conservation of mass and momentum, right? So the mass flux in is the mass flux out, etc. The tangential velocity are continuous, and there is the pressure difference is the momentum in the normal, change in momentum in the normal direction. Relative to the flame, Vf. Vf is, okay, so we have done that before. It's not enough to solve the problem because we need to know where the flame is or what's the propagation speed, and here is where the assumption of Landau and Darrieux is that the flame speed is the laminar flame speed. And so if I replace that here, it gives me an evolution equation for the flame front. Now, this seems to be a relatively simple problem, but it's not. It's what we refer to as a free boundary problem because we are solving equation with a boundary that we don't know. We have to sort of adjust it as we go along. So the surface is not known, and we have to satisfy this condition along the surface, okay? So it's, and furthermore, the fluid mechanics is not trivial because in general it's a nonlinear system, even the Euler equation, right, due to the convection term here. Okay, so let's see. Oh, I have to remember what comes next. So, you know, when you give a lecture, one lecture, you remember everything that is in the next thing. When you give 15, you don't. So anyway, what comes next is that I can simplify this, this Rankine-Hugoniot relation somewhat because of this flame speed relation. In other words, it takes only simple manipulation in addition to this by including that, remember the flame speed is V dot N minus Vf is SL. So if you add this, when you evaluate things on the right and on the left of the first equation, you can rewrite that the jump in the velocity in the normal velocity component is sigma minus 1 SL. Due to the expansion, the velocity and the burn gas is almost a factor sigma of the flame speed, okay? The tangential component doesn't change, and the pressure drops by that amount, okay? So this and these are equivalent. They're just a manipulation of each other, and I will use these in the future because it's simpler. Just something to note, which is important now. When they were equal to 0, it didn't really matter what is the difference of what with what in the jump. But now that it's not equal to 0, always my notation of the jump is burned minus unburned, okay? Because now we have a right-hand side, not 0. Okay, let's look at some simple situation. The first one is a planar flame. So for a planar flame, these are the Euler equation, including gravity in this case. So gravity in this picture is pointing downward, so the flame is propagating downward, okay? I'm sorry, the unburned gas is below, and gravity is pointing downward, so the flame is propagating downward. The flame is propagating into the unburned gas always, okay. So the Euler equation just tells you that the velocity is constant, and since in a frame of reference attached to the flame, the incoming velocity must be the laminar flame speed, then the burned gas leave at a speed sigma times SL. The density drops as you see here, and if I were to reverse this picture, in other words, if gravity was pointing, just turn it around, gravity is pointing up and the unburned gas is up, then in other words, if the flame is propagating upward, it's the same answer, it's just change G to negative G, okay? If you change D to negative G, you obtain the upward. At the moment it's not important, but tomorrow when we talk about stability, we're going to see that it makes a difference. The next thing I wanted to show is a slanted flame. So but suppose that the flame is slanted and it has an angle and it's steady. So if it's steady, then the flame speed is exactly equal to the normal component of the velocity, right? We defined that flame propagates in the normal to the surface. So this is by definition what the flame speed is, the v dot n. The star, by the way, in today's lecture and tomorrow lecture indicate evaluated at the flame on the unburned side. Okay, so the jump in v dot n must be sigma minus 1 SL. Geometrically is shown here. The incoming velocity is SL. This is much larger. I couldn't do it 6 times, so I did it approximately as whatever I could without getting out of the paper. The tangential component, which is the purple one, remain the same size, which indicate that if the flow is coming as shown here in the blue arrow, then it must be deflected by the flame, and this is the deflection angle, okay? It is always deflected towards the normal, all right? And you can even calculate the deflection angle if you're interested, all right? So the next thing is, let's say that we have a flame, I don't know the shape at the moment, but we have a parallel flow, steady parallel flow. So the flow is only in one direction. If the flow is parallel, that continuity tells you that u must be a function of y only. It can be only a function of y or a constant. Okay. Now again we have a steady flame, so the normal velocity in the unburned gas is SL. I am calling that interface x equal to f. I don't know why it's not shown. Below f is the unburned gas. F of y is the shape of this flame. And just at the flame, the normal velocity has to be SL. Okay, so now if I substitute this expression, if I just substitute for u, for v, I mean, in this expression, then the normal, well, I don't know why it's not written here. I thought it should have been. But anyway, the normal, it's easy to get. Right, there's no decent piece of chalk. So x minus f of y equal to 0 is the surface. right? So the unit normal is the gradient, so it's 1 and minus f sub y divided by the norm, which is 1 plus f sub y squared, okay? And so if you dot the velocity u by n, the only component you get is the u, and in the denominator you get that square root, okay? And that should be equal to SL. So all I just did the detail on the blackboard. And then the next thing is to solve, to rewrite, to bring the denominator up and to square the expression. So you get the f dy. And because you squared, you have a plus or minus. And it's equal to 1 over SL, the square root of u squared minus SL. And so if you want to solve for the shape, you integrate this function. And since fy is equal to x, right, then x is essentially that integral. So far, I left u to be general. So this is the flame shape if the flow is parallel. Let's first, what did I say here? To determine the flow field in the burn gas, it's not easy. One have to solve Euler equation, and it's quite complicated. But we're going to learn enough about the flame without solving in the burn gas. So in particular, one of the difficulty, as written here, in fact, in the bottom, is because as we shall see, the flow in the burn gas is rotational. The flame generates vorticity, and the equation becomes complicated to solve. So, but let's look at simple cases. So suppose that u of y is a constant, u. That is, you have a uniform flow coming. It's like on a Bunsen burner. Of course, I cannot discuss at the moment what is happening exactly near the rim, but above it is exactly what I have. I have a uniform flow coming. So I substitute for capital U in here. I get an exact relation that tells you x minus x naught is cosine theta y. Of course, plus or minus. I use the plus here and the minus here to construct the symmetric solution, that x equal to 0 in my notation is at the tip, okay? And theta is this angle. Well, the opening angle is the arc sine of SL divided by U. It's a well-known result, and we use that to experimentally measure the laminar flame speed as well. I will tell you about this in a minute. But one can also find that the same solution can be also the inverted flame, right? It can be an inverted flame where the slopes goes in the other direction. In fact, one can create an inverted flame in the laboratory. All you have to do is just to put a rod at the center to stabilize the tip, and then you get this inverted flame. So it depends if the flame gets stabilized at the rim or gets stabilized at this. And anyway, those two solutions are exactly what I have described here. Here is the Bunsen flame. You see that the unburned gas was seeded so as to show you the streamline. Streamline is quite parallel in the incoming flow in the unburned gas. Note that the flame is rather thin compared to that I found nice because it shows you what happens as you change your flow. Now remember that the angle was, it depends on the velocity, right? And so as you increase the velocity, you make the flame longer and more pointed. When you decrease the velocity, you increase the angle, make it flat, and eventually the solution that I had fails when SL become below U. In other words, when U become exactly equal to SL, you get a flat flame, as you expect. For U less, there is no solution, okay? In fact, you cannot have a stable solution, so it's not surprising that what you really have in what happens very often in the laboratory is that when the velocity go below, then you often have some flashback. In other words, the flame tried to flash into the burner. But those are unsteady conditions. And okay. So this is this. Oh, and so you see that when you reduce the velocity, the flame tried to be flat and flat. In fact, it never becomes flat. And the reason it doesn't become flat is, again, tomorrow. It's a Darry-Landau instability. Okay. You can, if you are interested, since the flow in the burned gas is rotational, complicated, but still it satisfies Euler equation, you can use a Bernoullis equation. But Bernoullis equation, only you have to be careful, it has to be along the streamline because the constant vary along streamlines, from one streamlines to another. And if you do that, you can get a sense of what the flow, the velocity look like far from the burner, because from this point, the blue point to here, the flow is uniform, and you can obtain exactly the relation between the pressure on one side, on one point and another. Then between 1 and 2, you can use the Rankine-Hugoniot relation to get the pressure change from the jump. And then from this point to this point, as long as you are along this streamline, you can again get Bernoullis equation. And if you manipulate the equation and so on, you can see what the velocity far is, and it takes a shape like that. But anyway, I'm not going to get further into this. It's just small comment. The next thing I want to say is, suppose the flow is not uniform coming out of the burner, but it's a Poiseuille flow. Well, still, the equation I just wrote before was valid because u was general. So instead of the little u of y, I will put Poiseuille flow or quadratic u. Remember that the u was squared. So in principle, what you had under this integral, it's u squared, which is square from Poiseuille flow squared, so it's to the 4th. So you get a 4th order polynomial. It turned out that you can decompose this polynomial in this form. So what you have in the square root is these two factors. You can write an exact solution for this if you want, but it's not that's not what I wanted to emphasize here. What I wanted to emphasize is that you're going to get essentially, instead of straight profile as we had before, you're going to get slightly curved profile, okay, with a sort of a cusp at the peak here at the top, at the tip of the flame. But the flame terminates here and here. It's not very strongly emphasized in the picture, but there is a line. Why does it terminate here and here? Because you see, y eventually will be, this factor will be negative and then the flame doesn't exist, or this factor will be negative and then the flame doesn't exist. What does it mean? Well, where the velocity, the incoming velocity in the Poiseuille flow, if this is the Poiseuille flow, if the incoming velocity here is such that the normal is smaller than the laminar flame speed, well, the flame cannot exist. Right? Because we said the speed has to be exactly the laminar flame. So it will only exist from part of the domain. Okay? Just a second. What really happened on the other side? Well, what really happened in reality is that what you have is, if these are so this is the solution, you get something like this on this end. What you get here really is that the flame extends in this way, and it's very similar to what I described to you before with the heat loss to the porous plug burner, okay? That due to the heat loss, the flame will get established at some distance, but of course it will eventually extinguish at some point because there's no fuel. Of course, this is not a very simple mathematical exercise to do. It's a computational problem that you have to resolve, and it's not very easy. Yeah?
I think you've answered it.
Oh, okay, good. And so the flame exists between those two regions. And see. If U is extremely large, U goes to infinity, for example, then, well, go to infinity relatively, then the whole thing simplified to a cubic. So you see that this cubic has a real well, I just said the word before, a cusp. Right. Okay, so this is this. Now, vorticity production. This goes back to a nice paper that was actually published in the 50s, and I thought just to quickly bring it in. It showed that if you write for a steady situation, if you write the Euler equation, which is written here, now this, there is a vector identity that you can replace V dotted with the gradient dot del with V by the gradient of V square and V cross the vorticity. It's a well-known identity which is basically used when you derive Bernoullis equation. So omega here is the vorticity. Because of this two-dimensional flame or two-dimensional setting that I'm looking at, there is only one component of omega which is out of the wall, right? So this omega is the magnitude and k is the unit vector normal to the wall. N and T are unit vectors normal to and tangential to the flame surface. So if you use this equation, decompose it into the normal and tangential component, and then use the Rankine-Hugoniot relation across, you can actually derive this expression that tells you that the change in vorticity from one side to another is related to the change in density, and it's proportional to the tangential gradient of the tangential velocity square, okay? It's not an obvious statement, but it's a result there. And if you apply it to a flame, then, I don't know if I have that. Yeah, if you apply it to a flame, then I wrote it in terms of sigma, which is the density of the unburned to the burned gas. So you see, even if the unburned gas is irrotational, the burned gas has vorticity created at the flame, and as a result, this is the amount of vorticity created. And sometimes it's useful to have this. The paper was done by Uberoy in 1958, and it's just quoted here. There are later on other derivation of expressions similar to this, but it's not, I don't need to add. Now it's useful because sometimes you can add it to this, and I will probably use it in one of the future examples that I'm describing. Okay, so here is another, here's the Bunsen flame. Usually, if it's well premixed, where you introduce the fuel and there is an air inlet, and then the tube is sufficiently long, as you see here, that allow for the fuel and oxide to mix quite well, then you would have a premixed flame established on top of the mouth of the burner. And since the laminar flame speed is related to the incoming velocity, if this is uniform, multiplied by sine theta, then you can measure the angle, and you know U, and you obtain the laminar flame speed. It's another way that people measure laminar flame speed. By the way, I show here a picture that you have a situation where maybe the mixture is rich, and so not all the fuel is consumed. Well, then you can have what we call a diffusion flame that is established the secondary flame surface, but we're going to talk about diffusion flame later. Okay, an expanding flame, spherically expanding flame. Well, if the flame, again, it's all in the context of this hydrodynamic theory. So if the flame is spherically expanding, continuity is written here, okay? the rho dt is 0 because rho is either constant on the unburned or on the burned gas. And since the velocity must go like 1 over r squared, clearly it must be 0 inside the sphere. In other words, the burned gas remained at rest. As the burned gas remained at rest, the flame propagated out and it pushed the unburned gas out. It's very similar to the closed tube that I showed you earlier. And so you can write a solution, explicit solution. You see the burned gas decay like r squared, and the flame position, capital R, is such that r dot, which is the propagation speed, this is like my VF, right? The propagation speed relative to the fixed coordinate, is sigma times SL, right? And which means that what you have, it's a linear, the flame radius vary linearly in time. You can also calculate, if you want, the pressure changes across the flame from the momentum equation. Here is a spherical flame that you see. I just noted that I put it here just to show you the dimension. Note that this is about 2.5 centimeters of the flame, which maybe it's part of this bright region. It's quite thin. Okay, so and here is the asymptotic solution. The temperature inside is the adiabatic temperature. Velocity is 0. Then you have a jump in velocity and the velocity decay like r squared. And the temperature outside is the unburned temperature. This is the profile of a spherical flame after it has propagated sufficiently to some distance. Numerically, it's a DNS. It's fully resolved, whatever propane air mixture. And this was done with single step, with multiple step, with one chemistry, another chemistry, a different mechanism, the different suggested, and all the results are practically the same. I will refer to that paper later on because it's one that I will illustrate some of the ambiguities in determining flame speed. But what you see, it's exactly the similar picture that I have here. Of course, there is no discontinuity, but the thing is resolved, but it's resolved on a very small distance, a small unit, in small length. Okay. Note, by the way, that the velocity decay much slower than the temperature decay. Takes much longer for the velocity to decay to 0 far away. What is interesting is that this is what experiment show. This is taken from a book by Strelo, which is, I think it's a nice book, but unfortunately it's old because Strelo passed away and didn't update it since. It wasn't updated since. But what you see is spherically expanding flame, propane air mixture at different equivalence ratio. And what is interesting is, what is interesting for us? Interesting for us is that when the flame is sufficiently large, it will essentially tend to an asymptotic limit where r dot is a constant, which is approximately sigma SL. Okay? And that's consistent with the theory. Why the asymptote is different? Because, of course, different equivalence ratio, the density change is different heat release, different temperature, and different adiabatic temperature, different density, different values. But what is interesting is that sometimes the flame accelerates from ignition towards this value, and sometimes you see decelerate. And the question for that will be addressed tomorrow. Yes?
I'm just curious, how much of an impact does changing the equivalence ratio have on the adiabatic flame temperature?
Well, it has, because we know that the adiabatic temperature essentially peaks at stoichiometry, and it's lower on one side than another. And so that's exactly the change that you see here, because the temperature is the reciprocal of the densities. Oh. Well, I mean, it's the only thing that you see here is the sigma. So it's, let's say from here to here, it's about a factor of 1.5. Well, it's not huge, but it's substantial, yeah. So that's, again, another way to measure laminar flame speed. As you see in this experiment, for hydrogen air, rich, I'll explain in a minute why. Propane air, lean, the flame is ignited by some electrodes at the center, and it propagates almost as a sphere, as a perfect sphere, up to 4.5 milliseconds here, 35 milliseconds here. So what you do, you let the flame propagate, and if it reach more or less the asymptote, you try to compute the propagation speed, divide by sigma, and get laminar flame speed. There's a problem with that, and the problem is there are two problems with that. One is if the flame becomes sufficiently large, sometimes become unstable. We'll discuss that tomorrow, and so you're measuring something which is no longer the laminar flame speed. And the two, some flame become unstable early on. For example, if I was doing hydrogen, not at 5 atmosphere, but at 1 atmosphere, and if it was not rich, it was lean, it would be immediately after ignition unstable, and so you're not going to get a spherical flame from which you can measure the laminar flame speed. That's why what you see here is the rich case, because the rich case is stable up to a certain distance. So instabilities will cause differences. Yes?
You reach absolute pressure at the center of this sphere.
I'm sorry, say that again?
You reach absolute pressure at the center of this sphere.
This is usually done at constant pressure, so they somehow ensure that there is a, any pressure get equilibrated somehow. When it's not a closed bomb, they try to do that by ventilated, I don't know exactly the experimental way of doing it, but was this what you're referring to?
We had an accident, 7 people died.
Oh, I see. Well, but the accident could be also because of if the mixture was subject to an instability, then the flame propagate faster, and it can very quickly, cause an explosion. So it could be also from the instability, not necessarily from the pressure, but yeah, pressure would certainly affect this. I had that example, but I took it out because of lack of time, where you can show how you can use the same theory for a flame expanding, but in a closed vessel, and how the pressure get built up, and including the flame speed that get built up. Okay, so this is now, sorry, I'm gonna take a few more minutes of your time today. I still have 5, but I want to do one more thing after this. So we have a spherical flame, and I want to introduce something which is simple at the moment, but tomorrow it will be more involved. So suppose that this flame is expanding, right? So its area is changing as it expands. So the area initially is 4 pi r squared. As the radius change, I can compute the time rate of change of the area, the ADT. And I can normalize it with the area, A. So if I compute this, it's going to be 2r dot, right? Divide by the same quantity, so it's 2r dot r. This is a rate at which the area is increasing or changing. That's what we call flame stretch. This flame is being stretched as it propagates. Okay? So in this case, it's being stretched, and then of course, as it becomes larger and larger, the stretch rate gets less and less. Eventually, it will be a large flame, almost like planar. Planar flame are not stretched, and so that's what you obtain here. Okay, very good. But not all flames are being stretched. If I was looking at this inwardly propagating flame, in other words, suppose that you have sufficient gas outside and the reverse, in other words, the unburned gas inside, I ignited somehow, outside. I don't know how you do that experimentally, but suppose you do that, and you let the flame propagating inward. This flame, the area will, the flame will be negatively stretched or will be contracted. So this flame will be negatively stretched. By the way, this flame is, you can describe the flow field. Now it's the unburned gas which is at rest. The burned gas is being pushed out. The burned gas is moving at this velocity, and the propagation speed will be, of course, negative SL just for the convention of the use. So this flame is negatively stretched. Okay, by the way, this is a very, I said, you know, I don't know how you do it experimentally, but if you look at a Bunsen flame, and I drew most of it before by using the simple hydrodynamic theory, of course it doesn't describe what's going on here, what's going on near the tip. The tip is usually rounded, is not, you don't get a cusp in reality. What you get at the tip is exactly something similar to this converging flame, okay? So the physics here is exactly this physics. The flame is being negatively stretched near the tip. The example I wanted to quickly show you before I stop today is the counterflow flame, a very useful configuration used very often in experiment because the flame is flat. That's the main reason. It's a simple configuration. The flame is flat. And you can obtain this obtain different version of it. So for example, you can have an inert gas and a combustible mixture. So you're going to get a single flame. The inert gas can be injected at a temperature which is close to the adiabatic temperature. So you have the stagnation plane here will be let's say held adiabatic, so you can produce a adiabatic condition, or if you don't, then you don't. But I mean, you have a lot of option. You also have the option to provide the same combustible mixture on both ends, and then you have twin flames, and you have a variety of other things that you can do. Of course, to get this configuration, the burner must be well aligned, and there's little other things that you have to worry about, but this is quite nice because the flame is flat, and so you can take measurement in few places, and you don't have to, you know, spend the entire flame surface. Okay, it's of course similar to a flame in a stagnation point flow, okay, because it's just a symmetric thing. Now, the incoming flow in a stagnation point flow is well known in fluid mechanics. It's essentially a linear increase in the axial velocity, and then the velocity in the transverse direction. Well, this is axisymmetric, so the velocity in the radial direction is proportional to the radius, and epsilon is what is called what is known as it's a strain rate. So this is the strain rate, and this is the velocity. Now you notice that here I have changed a little bit the solution by putting a z minus a. I included a displacement. The reason for this is the following. When you have a flame, you have vertical motion here, and this vertical motion displaces the incoming flow. And it displaces at a certain distance, a. And so we are going to see how much it is displaced when we solve the problem. Okay, so but this is the idea. There is a displacement. And in fact, you see what I drawn here. If the flow was to continue, if the streamlines were to continue without being deflected by the flame as they are, then they will be diverging along this surface, which is displaced from the real stagnation point. Okay, so the flow in the incoming flow is known. The flame position is not. and this displacement is not, but we are assuming that the velocity just ahead of the flame is the laminar flame speed, so we can solve this problem. Remember that the flow in the burn gas is not potential, so we have to solve the vertical motion there. So I'm going to use exactly that jump relation of vorticity that I created before. And so I have now the jump in the axial velocity, the tangential velocity, and the vorticity. I'm going to go through the detail rather quickly given the time. But since I have the jump and I know the solution upstream, right, ahead of the flame, I can just write those for being conditioned downstream, namely in the burn gas. So I know that at the flame in the burn gas, U is this, V is this, omega is this, okay? So now I want to solve the burn gas. Those are the Euler equation. I am going to run through this quickly. As I said, I can introduce what is known as a stream function. And since the vorticity is related to the stream function, I'm using what it's called vorticity stream function formulation. So I can rewrite the vorticity equation as a single equation for the stream function psi. It's a simple way to solve the equation because then you don't have the pressure term to deal with. Okay, so you increase the derivatives, but you eliminate the pressure. The pressure is eliminated because when you take the curl of the momentum equation to get the vorticity equation, the curl of the gradient of P is 0. Well, in this case, things are even simpler because the vorticity divided by R is conserved, and the vorticity divided by R is a constant, so immediately you can write the answer. As I said, I will jump here and write that and just tell you the solution. This is what you get for the stream function, and the solution is a quadratic function in Z instead of the linear solution in the absence of combustion. And here are the profiles. So here is, in fact, the entire summary of the solution. The incoming flow is coming, increase the velocity as you approach the wall, decrease, up to where the flame is. There is a jump in the velocity across the flame, and then it continued to decrease, but this time not linearly, but parabolically. And that's the solution. The flame distance is given here, and the displacement is here. By the way, if sigma is 1, meaning no density change, no displacement, 0, right? Sigma 1, no combustion, there is no displacement. Okay. The pressure also can be calculated, and I will skip that. Here is an experimental picture where they took that theory and put it, they took the asymptotic theory, the black curve, and stuck it here along with the experimental data. Clearly, in the experiment, the flow does not come from negative infinity, come from a nozzle, so it comes from, it is uniform at some point, but eventually, you know, you get that linear dependence which determine for you the strain rate, so that's fine. As a matter of fact, they didn't really do justice to the theory because I would have done it like this. And the reason for it is not just because it's nicer and it fit better, because I would put the flame or the reaction, the flame sheet where the reaction sheet is, because that's where they shrink. And in fact, tomorrow you will see that I would argue that that's the correct way to do it. But it doesn't matter. This way or that way, the theory is well respected, I think. So this is my last slide. I think it is my last, and that's why I wanted to get to it. I argue that this flame is also stretched. Now, what we said before is stretch is a relative area change. Well, let's do that. You're not going to find this in any textbook, by the way. So here is the area. So remember that this is an axisymmetric flame, so the area is just pi r squared, where r is the flame, let's say, the radius that I'm choosing. So the ADT is the area at T plus some delta T, and the minus AT divided by delta T, by definition of a derivative. I can calculate A at a given time, which is pi r squared. This should have been a little r. There is no capital R here. A little r is just the position, right? And at a later time is going to be r plus delta r. But what is delta r? The change in delta r is due to the tangential velocity, which is v delta t. So now if you manipulate that and you divide by delta t, you get that the limit is 2 pi rv. In other words, the stretch rate, it's exactly the strain. In other words, the velocity stretched the flame. So we have seen that flame can be stretched for two reasons. One, because their area increase as the flame propagate, and second, because the underlying velocity can just stretch the flame, okay? At least the hypothetical surface that we call the flame, right? I think that's the last one. This was just to say that this is used, by the way, experimentally to also obtain the laminar flame speed, but this is going to be better understood tomorrow when I talk about flame stretch and stretch flame. So we have seen that flame can be stretched in two ways. Now a general three-dimensional surface would have both. Would have the fact that the curvature changes and therefore it's stretched by that, and it also stretched by the underlying flow field, which is like this. So these are two like classical examples that illustrate stretch. Thank you.